Approximations of diode. When diode is used in the circuit and when the circuit analysis has to be done, it becomes easy if some appropriate approximations are made. These approximations are used depending upon the circuitry and the accuracy with which the results are required. There are three different types of approximation, that is first approximation, second approximation, and third approximation. And based on what type of accuracy we need, we can use any of these three approximations. Starting with our first approximation, here in the first approximation, our diode is considered as an ideal diode. So in an ideal diode, whenever we are connecting our diode in forward bias, this ideal diode will act as a perfect conductor with zero resistance. And under reverse bias condition, it acts as a perfect insulator with infinite resistance. When we say it is a perfect conductor with zero resistance, we can replace or we can find the equivalent of the diode as a closed switch. Similarly, in reverse bias condition, when we are calling it as a perfect insulator with infinite resistance, we can replace the diode as an open switch. That means it will not allow the current to flow. Here, we are not considering any depletion region or junction barrier across our diode, which resists the flow of the electric current. So during during forward bias, we will be getting the output current, whereas during reverse bias, we are, as it is acting as an open switch, we are not getting any output current. So this is the VI characteristic of our first approximation, or we can say it is a VI characteristic of an ideal diode. Now, doing the comparison between your ideal diode and the practical diode, we can say that ideal diode act as a perfect conductor and perfect insulator, whereas practical diode cannot be your perfect conductor and insulator. Ideal diode draws no current when reverse bias, whereas practical diode draws very low current when reverse bias. We had already seen the VI characteristics of the diode, in which we can see that even if we are connecting our diode in reverse bias, initially we are having a very small and a constant reverse bias current. Next, we can say ideal diode offers infinite resistance when reverse bias, whereas practical diode offers very high resistance when reverse bias. Ideal diode cannot be manufactured, whereas practical diode can be manufactured. Ideal diode has zero cut-in voltage. Practical diode has a very low cut-in voltage. That is, we have seen in that for Si, we are having 0.7 cut-in voltage, and for germanium, we are having 0.3 cut-in voltage. Ideal diode has zero voltage drop across its junction when forward bias, whereas practical diode has very low voltage drop across its junction when forward bias. So this was the basic comparison between your ideal diode and practical diode. Now moving forward to our next approximation, that is second approximation. Here in second approximation, we are also considering our next term, that is barrier potential, which was initially ignored. So the equivalent circuit of the diode when connected in forward bias is a closed switch, plus we are considering the barrier potential, that is 0.7 for silicon and 0.3 for germanium. So we can say that because of this barrier potential or the battery we had connected over here, when the diode is in forward bias, it cannot conduct and no current flows until the applied forward voltage reaches to 0.7. When the applied voltage is 0.7 or more than 0.7, we'll be getting the output, but till then your diode will not conduct and we won't get any output. Now, whenever we are connecting our diode in reverse bias condition, it will act as an open switch and in the output we won't get any output. This is the VI characteristics of your second approximation. Here you can see that in forward bias, till your input voltage is greater than 0.7, we won't get any output. On 0.7 for SI or 0.3 for GE, we are getting the output, right? So we are considering the barrier potential in our second approximation. And in reverse bias, as it is acting as a open switch, we won't get any output. So this was about your second approximation. In second approximation, we are considering another parameter, that is barrier potential. Whereas in the first approximation, the equivalent of the diode is only as a switch. Whereas in the second approximation, we are considering switch as well as we are considering its barrier potential. Now moving forward to the third approximation, in which we are adding another term, that is our forward resistance. So here you can see that the equivalent circuit for a third approximation of the diode is switch plus barrier potential plus your forward, or we can say bulk resistance. Here, initially, as we saw in the second approximation, till 0.7, we won't get any output because of this barrier potential, and after that we'll be getting the output linearly. Here the output voltage is equal to the summation of your barrier potential plus your forward voltage drop across your resistance, that is IF into RF, right? So the total output voltage will be equals to V0, that is barrier potential, plus your voltage drop, that is IF plus RF. As we are considering our forward resistance in our equivalent circuit of the diode, we'll be having some voltage drop across this resistance. So in the output of the graph, you can see that till 0.7 we won't get any output, and after that our graph output current increases gradually. Again, in reverse bias, as the equivalent of the diode, it will be an open switch. We won't get any output in our reverse bias. So this is the VI characteristics for your third approximation of the diode.